Sorry guys, I don't know what's happening with my network, but I'm just hoping that we'll be able to finish up this paper. So we were now doing question number 2.33, where they say that a note on this sound wave with the same speed is played at a higher pitch than before. How does this affect the following? Write down increases, decreases, or remains the same. So when you're given pitch, you should know something. Let me just make space so that we can find somewhere to actually get what? To illustrate this correctly. So we are saying that whenever we are given pitch, there are things that we need to know regarding pitch. So let's say this is our wave. When now we have got a higher pitch, it simply means that that same wave would have a higher frequency, which means that it will have more waves per unit time. We are going to increase the number of waves per what? Per unit time. So it's more like we are just saying that we are going to have, let me draw this. Whilst this side, you are just having what? Things like that, right? So we are saying that this is when you have got low pitch. Whenever you have got low pitch, you have what we call a longer wavelength. Whenever you have got low pitch, you would have a longer wavelength. Whenever you have got a high pitch, when you have got a higher pitch, when you are having a higher pitch, you are going to have a shorter wavelength. This corresponds to high frequency. And then this side, low pitch, corresponds to low frequency. But what happens is the amplitude should remain the same. The amplitude is not affected by pitch. So the amplitude remains the same. So that is what I wanted to illustrate there in terms of pitch. So whenever you have got high pitch, just know that you'll be having what? A higher frequency and a longer wavelength. Now they are saying, does the amplitude of the new wave increase, decrease, or remain the same? The amplitude will remain the same. The amplitude will remain the same. What about the distance between A and B? A and B, we saw that it was distance between a compression and a what? And a rarefaction. This corresponds to what? To wavelength. So that distance is actually going to decrease. Why is it going to decrease? Because we say that whenever we have got a higher pitch, we have got what? A longer wavelength. So we are saying that this is going to what? To decrease. The distance here is going to decrease. A higher pitch, and then we have got a what? A shorter what? A shorter wavelength. Would be having a shorter wavelength, a higher pitch and a shorter wavelength. And then for the period of the wave, period, we know that frequency can be given as 1 over t. Therefore, we know that t can also be given as 1 over frequency. Whenever the frequency is high, the period will be low. So our period is going to decrease. Why? Because we have got what? Increased what? Increased frequency. Whenever the frequency gets to increase, then the period will decrease. So this one would also decrease. Now let's look at the following question. Question number 3 is saying, what is meant by the dual nature of electromagnetic radiation? So it simply means that electromagnetic radiation can behave as both a particle and a what? And a wave. Can behave as both a particle and a wave. So when we say it can behave as both as a particle and a wave, as a particle, it will be carrying packets of energy. It will be carrying what? Packets of what? Of energy. When it carries packets of energy, these packets are called what? Photons. And then as a wave, it will have what? Frequency, it will have wavelength, which would actually get to translate to its what? To its velocity. So electromagnetic radiation can also have energy as well as the what? As the wavelength. So here they're saying define the term photon. So a photon is just a packet of what? Of energy. Is a packet of energy. A packet of energy that is carried by electromagnetic radiation. So it's just a packet of energy. Now they're saying calculate the wavelength of this photon. So you are given that E, which is your photon, is equal to HF, where H is Planck's constant, and we know that Planck's constant is given by 6.63 times 10 to the power negative 34. And F is our frequency, where frequency from our wave equation can be given by the speed divided by the what? By the wavelength, where this speed becomes the speed of light. So this equation can actually translate to hc over lambda. So when we are looking for the wavelength, which is lambda, we can say hc over the energy of that what? Of that wavelength. So our wavelength can actually be given by, we are given, we know h, which is 6.63 times 10 to the power negative 34. And then c, which is the speed of light, is always what? 3 times 10 to the power 8, which is 3 million meters per second. And then the energy that is given, it's 5.95 times 10 to the power minus 16. So if you do that, let's punch our calculators. When we punch our calculators, we are supposed to get an answer of 3.34 times 10 to the power minus 10 meters. So that is how you would have calculated your wavelength. Now they're saying that will the wavelength of a photon with a higher penetrating ability be less than or equal to or greater than the one that we have just calculated? Okay, fine. Now we need to know something to do with what? With the penetrating what? With the penetrating ability. The penetrating ability, it's a property that the electromagnetic spectrum has. So on your electromagnetic radiation spectrum, you have got different waves. Like for example, we have waves that we refer to as what? As gamma rays. So we have got gamma rays. And then from gamma rays, we come to X-rays. From X-rays, we then come to what? To UV light, which is ultraviolet. And then from ultraviolet, we come to infrared. From infrared, we come to microwaves. From microwaves, we then come to what? Radio waves. So now, within all these are characterized by different what? Wavelength and frequencies. So you would see that the wavelength of these decreases, it increases as we go to what? To radio waves. So the wavelength increases as we go from gamma rays to what? To radio waves. Whilst frequency decreases as we are going to what? To radio waves. So this is where we've got the ranges. And under gamma rays, the range should be what? 10 to the power minus 6 nanometers. And then here for X-rays, the range should be what? 10 to the power minus 5 nanometers. For UV light, we are supposed to actually get to what? Now I'm just I'm saying here we should have from 10 to the power minus 6 to something like 10 to the power minus 1 nanometers. So this one is 10 to the power minus 6 to what? To 10 to the power minus 1 nanometers. And then for X-rays, they are now starting there, 10 to the power minus 1 up until we reach what? 10 nanometers. And then for your UV light, this is where you've got 10 nanometers to something like 1000 what? Nanometers, which is just 1 micron. So we have got 10 nanometers to 1000 nanometers. And then infrared now, infrared will now be having what? 10 micrometer to something like, which is what? For infrared, something like 1 millimeter. And then here on your microwaves, you'll be having something from 1 millimeter or else 10 millimeters to something like 100 millimeter to 100 what? 100 meters. 1 millimeter to 100 meters. 1 millimeter to 100 meters. And then radio waves are the ones that starts from what? From a kilometer to something like 100 kilometers. So we want to see that they are saying, will the wavelength of a photon with a higher penetrating ability be less than 3 times 3 to the power 4 times 10 to the power minus what? 10. So the one that has got a high penetrating ability is gamma rays or else X-rays. So we are saying that this one, which is having this this wavelength, actually falls under which one? It actually falls under UV light. It actually falls, sorry, under X-rays to UV light. So the one that has got a higher penetrating ability is going to have what? Is going to have what? Smaller than, or else let's say less than what? The wavelength. It is going to have a lesser wavelength. Anything that is having a higher penetrating ability is going to have what? Lesser than. So you should be familiar with this. You should be familiar with this. However, though, someone would have just said that anything that has got a higher penetrating ability should be having what? A lower or else a lesser wavelength, without going all this trouble of remembering this. But this would actually give you a kickstart of understanding what is penetrating ability and wavelength. So anything that has got a higher penetrating ability will have what? Less than the wavelength that is given there. That was the answer there. Now let's go to 3.4. Else, let's go to question number 4. So that was the final for question number 3. Now question number 4 is saying we've got two identical charged spheres, which is sphere A and sphere B. Now we are on electrostatics. This is electrostatics. They are saying that sphere A and sphere B, they are placed on an insulated stand, and sphere A has got that charge, -8 nanocoulombs, and then sphere B has got positive what? 3 nanocoulombs. So let me just get to bring it up because you can see that the diagrams, they represent every information that is given there. Let's hear what the questions are saying about those two spheres. The first question is saying, calculate the number of excess electrons on sphere A. So we know that the number of electrons is given by the what? Charge per electron. Or else charge divided by the what? By the charge of an electron. So the charge of an electron is given as -1.6 times 10 to the power negative what? 19. Let's just, I actually have got information sheet here. We can use that so that people, they would you would actually get to see where I'm taking it from. So this is the charge of an electron. It will be given on your information sheet, and this is the Planck's constant that we have been using, and this is the speed of light, and then that becomes the acceleration due to gravity. And then after that, you have seen that the charge of an electron is what? Negative 1.6 times 10 to the power negative 19 coulombs. And then let me show you something else as well. So on this one also, we can see that these are the equations that we have been using, this one and that one, as well as that one and that one. So everything, this is the wave equation, this is the photon, and then this becomes your frequency after manipulation, frequency with period. So everything would be given on your what? On your information sheet. I now want to also show you. So let's go back to our question. So now we know that the number of electrons are given by the charge divided by the charge of an electron. Charge of an electron is that, and then the charge that is given, it's negative 8 times 10 to the power negative 9. Why? Because nanocoulombs, it's times 10 to the power negative 9. When we divide how many extra or excess electrons does sphere A has? So when you divide, the answer that you're supposed to find there should be what? It should be simply 5 times 10 to the power 10 electrons. So you just need to divide those. Now they're saying the charges touch and are separated after a short time. So when these come into contact, they are going to actually get what? To share the charges, distribute the charges equally, and then they are actually going to what? To separate, and then each would go with the half of the total of the charges. But however, let's hear what they are saying here. State the principle of conservation of charge. The principle of conservation of charge, it states that in an isolated system, total charge is conserved or constant. Total charge would be what? Will be conserved. That is in an isolated system. So if this system is conserved, if this system is isolated, the total charge will be conserved. Now they are saying, calculate the new charge on each sphere after touching. So after touching, when they touch, we add. That is to say, total charge will be equal to what? Negative 8 nanocoulombs plus 3 nanocoulombs. And we are going to get what? Negative 5 nanocoulombs. When they separate now, each is going to have equal charge of the total. Equal charge of the total. So we are simply saying that we now need to divide the total by 2 to have each charge of each sphere. So now after separating, charge of each will be equal to negative 5 nanocoulombs divided by 2. And that will actually get to give us what? It will give us negative 2.5 nanocoulombs, which is also equivalent to what? Negative 2.5 times 10 to the power minus 9 coulombs. That is what we are just supposed to do there. That is for 4.22. Now they're saying, after touching and being separated from sphere B, sphere A is now brought closer to another identical sphere C, which is neutral. Will there be attraction, repulsion, or neither? Give a simple scientific reason for your choice. So after separation, we are having what? Sphere B carrying a charge of what? Negative 2.5 nanocoulombs. And then it is brought about on sphere what? Sphere C, which is neutral. So a neutral would be having equal number of what? Positive charges as to negative charges. So what is going to happen is we are going to have what we call partial polarization on this sphere, where all of the negative will be repelled to that other side, whilst all of the positive will be attracted to this other side. So we are going to have, let's say these are negatives from this, from sphere B, and then on sphere C now, you are going to have negatives this side, and then you are going to have positive, you are going to have the positives are the ones that are actually going to be what? Are actually going to be attracted this side, whilst the negatives are repelled. So due to this partial polarization, there is going to be what? Attraction. So here you're going to say attraction, and then the reason is there will be partial polarization. So you would say that there will be partial polarization where the negative charges will be partially repelled to the far side of the what? Of sphere C, where the negative charges, so where the negative charges of sphere C will be repelled to the far side of C. You can add by just showing what you are saying, so that you can say if this is sphere B and it is having a charge which is negative, we are going to have positives being attracted this side and then negatives being what? Repelled to that far side. So that is what is going to happen there. Due to this, we are going to have what? We are going to have what? Attraction. We are going to have what? Attraction. So that is what we are supposed to say there. Now let's go to question number 5. Now we are now given a basketball player. They are saying that he runs around the basketball court during a transmission session, during a training session, sorry. And then we can see that this is the basketball court, which has got a length of 30 meters, a breadth of 15 meters. In one of such sessions, he runs from A to D, then back to the center line from D and goes back to D, finally back to A. So they're saying that he runs from A and then he goes to D. And then he comes back to the center line. And then he goes back to D. And then later go back to A. And they're saying calculate the total distance covered by the player. They're saying calculate the total distance covered by the player. So you would see that he ran 30 meters plus he later ran 15, 15, another 30, plus going back another 30. So the total distance there, the total distance moved by the player is just equal to what? To 90 meters. Now let's see the following questions. So the player moves what? 90 meters. He runs 90 meters. During that motion of his, 90 meters. That is what we are supposed to do there. Calculate the time it took the player to complete the session if his average speed was that. So we know that speed is given by the total distance divided by the total time. So here they're saying calculate the time. So we want time. So we interchange time and speed there. So it will be distance divided by the what? By the speed. So we know the distance that he covered, which is 90 meters. The speed is what? 2.5 meters per second. So the total time there is supposed to be what? So we now need to say 90 divided by 2.5. So let's punch our calculators. That will be 36 seconds. So the total time there would be 36 seconds. So you just use the equations that you know. You know that speed is equal to distance divided by time. And then if you're given speed and distance, you just substitute them and then you manipulate to find t. So your time there is just what? 36 seconds. Now they're saying define the term average velocity. Average velocity becomes what? The rate of change of position, or the rate of change of what? Displacement. So your average velocity is the total rate of change of position. Total rate of change of position, or else rate of change of what? Of displacement. And then they're saying determine the average velocity of the athlete. The average velocity of the athlete, where we are saying average velocity, would be equal to the change in position divided by the time. But here he moved from A and then he went to D. He came back to the center line. He went back to D and then later came back to A. So he did not change his position. So the average velocity here becomes what? 0 meters per second, because he did not change any position. 0 there. It's 0. Let's go to the next question. Question number 6, which is saying that the change in position versus time of a motorbike that moves originally in the easterly direction is measured and the following values were obtained. So we are saying that time and position. And then they say use the information in the table and draw an accurate position time graph on the graph paper indicated. So what we're just supposed to do there, it's unfortunate that I don't have the graph paper here. I would have shown you on the graph paper. But however, let's say that you are given something like this. So you'll be having boxes on your graph paper, both on your x-axis and your y-axis. So whatsoever is on the y-axis is what? Position, which is in meters. On the x-axis is what? Time. Let's say time is the one that is on the x-axis, which is in seconds. And then you know that it's 0, 0, time 0, there is no position, or there is no change in position. After 1 second, let's say this is 1, from 0, and then 2, 3, 4, 5. And then let's say we go with 5, 10, 15, 20, and then 25. After 1 second, the position is now 5 meters. After 2 seconds, the position is what? 3, it's 10, 3, 15. So I'm sure you can see that this was just going to be a straight line, a smooth straight line. That is what you were just supposed to do there. Draw your position in on your y-axis, your time on your what? On your x-axis, and then plot these points where you plot 0 and 0, 1 and 5, 2 and 10, 3 and 15, 4 and 20, 5 and 25. Now they are saying calculate the gradient of this graph. The gradient is just what? Change in x, change in y over change in x. So if you are now calculating gradient, so on the gradient there, I was just going to say gradient, which is represented by m, is what? Y2 minus y1 over x2 minus x1, where y2 would be this value, 25, minus y1, that value, because we are at position 1 and position 2, 0, divided by 5 minus 0, 5 minus 0. And then the gradient there was just going to be 5. So that was going to be equal to 1.12. That was for question 6.12. Write down the value of the acceleration of the motorbike. The acceleration of the motorbike, when position time graph has got a constant straight line, it means that the velocity there is constant. Velocity is constant. When the velocity is constant, it means that acceleration is equals to 0. So the acceleration of the motorbike was 0 meters per square second. So you just needed to come and say what? 0 meters per square second there. 0 meters per square second. In another motion, now we are given another motion. In another motion, so let me bring it up because it's now a different question. In another motion, the motorbike accelerates from 0, which is rest, at an average acceleration of 2.5 meters per square second for 10 seconds until it reaches a certain velocity. Calculate the magnitude of the velocity that the motorbike reached after 10 seconds. This is where you use your equations of the motion, which is motion in one dimension, where V final can be given by V inlet or else V initial plus acceleration times the change in time. Or else you can come and say V final squared is equals to V initial squared plus 2A delta X. Or you would have just said what? Average velocity being equal to V final plus a V initial over what? Over 2 times delta X. But however, here they want us to find what? Calculate the magnitude of velocity that the motorbike reached after 10 seconds. So we have got initial velocity, which is equal to 0 because it's starting from rest. And then we have got acceleration, this one, and time. So we can simply use that one. So for 6.21, we're going to use that equation, substitute 0 there, and then here acceleration 2.5 times the time 10. This was going to be equal to what? 25 meters per second. Now they're saying calculate the distance that the motorbike covered in 10 seconds. 6.22. The distance that the motorbike covered in 10 seconds. This is where we can either choose this. We now have got the final velocity and the initial velocity. We can calculate that. Or else, this is where we can actually use delta X is equal to what? VIT plus half of the acceleration delta t squared. So we know the time that it takes. So we can say delta X is equals to initial velocity is 0, the time it's 10, plus half of the acceleration, which is 2.5 times 10 squared. So you would see that this becomes 0 plus 2.5 times 100 divided by 2. This actually becomes 2 into 100, it's 50. 50 times 2.5, 50 times 2.5, it will give you 100 and what? It will give you 125 meters. So you were supposed to find the distance of what? 125 meters. 125 meters. That was that for question number 6. Now let's go to question number 7. A small ball with a mass of 900 grams rolls down from rest along a frictionless surface AB. Point B is 7 meters below the starting point. The ball continues its motion from point B to C, where it experiences some frictional force and finally comes to a stop after covering a distance of what? 10 meters. And they are saying that the motion of the ball is shown in the diagram below. So this is the motion of the ball. So let me just take it up because we can see that everything that is said in that paragraph is there on that what? On that diagram. Now they are saying calculate the gravitational potential energy of the ball at the height of 7 meters above the lowest point. So how do you calculate gravitational potential energy? You know that potential energy can be given by mgh. So we need to know the mass at point A and the height at point A. We need the mass, the height, and the gravitational acceleration. So the mass there, it's 900 grams. 900 grams, we need to transform it into what? Into kgs. So we divide by what? By 1000. So this is going to be equal to 0.9 kgs. And then that becomes our mass. Our height is equals to 7 meters. And then the gravitational acceleration is simply 9.8 meters per square second. So that is what we are going to substitute here. We are going to say 0.9 times 9.8 times 0.9. And this was going to give you what? It was going to give you a value. If I punch my calculator, it was supposed to give me a value of 61.74 joules. 61.74 joules. So you were supposed to find 61.74 joules. That was the potential energy. Like that. So that is how we calculate our gravitational potential energy. Now the following question is saying, state the principle of conservation of mechanical energy. The principle of conservation of mechanical energy, it simply states that mechanical energy will always be conserved in a what? In a closed system. Or else you would say that in a, let me remove what is on top there. You would say in a closed system, in a closed system, the total mechanical energy will always be conserved. Will always be conserved, or else would be constant. So that is how you can answer that. Will always be conserved, or else it will be what? It will be constant. That is the principle of conservation of what? Of mechanical energy. Now they're saying, is mechanical energy conserved from A to C? Write down yes or no, give a reason. From A to C, it's a frictionless surface. Yes, the total mechanical energy is conserved. But from B to C, it has got friction. Due to this friction, this is a this is a dissipative force. So the total mechanical energy here is not conserved. So you would say that no, it is not conserved. Why? Because from B to C there is friction, which is a what? Which is a dissipative force. So because from B to C there is friction. Once there is friction, it's as if we have opened our what? Our system to dissipative forces. Now calculate the magnitude of the average acceleration experienced by the ball from B to C. The magnitude of the acceleration from B to C. How do we calculate that? So what I would advise is you need to first calculate velocity which the ball will reach with at point B. Because at point C, the velocity there is 0. And you are given this distance. So you can use your equations of motion. But what you need to do is to what? Is to calculate the final velocity at point B, which is final velocity at point B. And that becomes your initial velocity. So we need velocity at point B. How do we calculate velocity at point B? We can use the law of conservation of mechanical energy from point A to point B, where we are saying total mechanical energy at point A should be equal to total mechanical energy at point B, where total mechanical energy at point A is given by potential energy plus kinetic energy at point A, as well as total mechanical energy at point B is given by the potential energy at point B plus kinetic energy point B. So potential energy at point A is given by what? The one that we calculated, we said 0.9 times 0.9 times 7. Sorry. We are supposed to say, now I'm now using 0.9. 0.9 it's for mass, 9.8 times 7. And then the kinetic energy at point A is 0 because it is at rest initially. Potential energy at point B is also 0 because the height is now 0. And then kinetic energy now is the one that is equal to half the mass 0.9, and then the velocity at b squared. So now we can find the velocity at b. Velocity at b now will now be equal to the square root of everything that is this side divided by half of that. So it will be 0.9 times 0 times 9.8 times 7 divided by half of 0.9. We just divide throughout by that and then we square. So the velocity at b was supposed to be equal to, it was supposed to be equal to what? So here, let me just get to try to find somewhere clear where you can see what I'm doing. So I'm saying velocity at b would be equal to this, in this bracket, 0.9 times 9.8 times 7, all divided by what? By half of 0.9. And everything has to be squared. It has to be square root. You need to square root everything here. So VB, the velocity at B. So the velocity at B was actually going to be equal to, velocity at B was going to be 11.71 meters per second. Now, after finding velocity at B, we know velocity final is equals to 0. So we can use final velocity is equals to initial velocity, which is final velocity squared, initial velocity squared, plus 2 acceleration times what? Delta x. Final velocity, it's 0 because it comes to rest. Initial velocity there is this velocity, which is 11.71 squared, plus the acceleration here would actually be what? Uh, we say 2 times acceleration times the displacement is what? It's 10. Now we now need to manipulate our equation so that we can find what? Acceleration. So we're just going to transpose and later divide. So our acceleration is supposed to be a negative, as you can see there. So if I take this one that side, this one that side, it will actually be what? 2 times a times 10 is equal to 11.71 squared. And then I divide throughout to find a, or else make a the subject. 11.71 squared divided by 2 times 10. And then that one was going to give us an acceleration of 6.86 meters per square second. So that is how you would have calculated the what? They said calculate the magnitude of the average acceleration experienced by the ball from B to C. It was carrying 6 marks. You first calculate the velocity at B and then later calculate the acceleration using the equations of what? Of motion. Now let's go to question number 8, which is our final question. They are saying that in the circuit diagram below, switch S is open and the reading on the ammeter is 1.5 amps, whereas V1 reads 6 volts. So they've given us a diagram. So let's see this diagram. It represents everything that has been said there. So this is where the ammeter reads 1.5 amps, and this is where the voltmeter V1